Okay, so for this first conversion, we're going to look at a skater that rolls down a ramp to the ground here. Let's just take a look at what happens first. All right, so there's our motion. We're going to return the skater back there. Let's go ahead and put some bar graphs on here. Put these over here. And we'll remember that when we see potential, we're talking about stored gravitational energy. When we see kinetic, we're going to talk about energy of movement. Those are just other names for them. So notice right now that the skater's energy is all in the stored gravitational flavor. All right, and we're going to let it roll here, and we'll watch that go. All right, when he gets to the bottom of the ramp, we've lost all of our gravitational, and it's been converted to kinetic or movement energy. So we're going to go ahead and look at a couple ways that we can quantify some of these values. Okay, so this is just a couple images from the video we just watched. We see that when the skater is at the top of the ramp, up here, all the energy is stored in gravitational. When the skater is at the bottom of the ramp, all of it's stored in energy of movement. Now, we've done this before, but here we're going to start to challenge ourselves and say, what is the quantitative conservation energy equation for this example? Well, it's pretty simple. We just know that whatever gravitational was at the start needs to equal the energy of movement at the end. We look at this line up here. This line up here represents the total energy. And so Eg is equal to Em, and they're both equal to the total energy. So we have this equation here. Now we can expand this equation, and we can plug in values that we already know for these equations. We know that Eg is equal to m for the mass times the acceleration due to gravity, 10 meters per second squared, multiplied by the height of the object. And that's going to equal the energy of movement. We know the energy of movement is equal to 1/2 the mass times the velocity squared. This here is our quantitative conservation energy equation. Just like I've said, it doesn't take one form. It can be many different forms. Okay, if I move down here and give us this information, I'm going to ask now, can we solve for an unknown value? What if I wanted to know how fast the skater was moving at this point right here? How fast? Well, with these tools, we can actually figure that out. We know that the mass times the gravity times the height must equal 1/2 times the mass times this velocity squared. We're looking for this v in this example. So let's plug in what we know and see if we can solve for that. The mass of the skater is 75 kilograms, multiplied by acceleration due to gravity, 10 meters per second squared, multiplied by the height, which is 6 meters. And this should equal 1/2 the mass of 75 kilograms, multiplied by, we don't know the velocity, so keep it a variable, 1/2 v squared. All right. When we do this, there's one thing that really comes out very clearly. When we do a gravitational to a movement energy, we notice that mass ends up on both sides of the equation. This is a little trick. The mass gets canceled out, and what that actually says is that the mass does not matter. The mass does not matter in a perfect transfer of energy. So you can notice that really quick. If we multiply these things, we see 6 times 10 is 60. I'm going to drop my units for simplicity. Is 1/2 v squared. Put the 1/2 to the other side, you multiply this, you get 120 equals v squared. Then you just have to take a calculator, and let's say we take 120 and take the square root of it. You see 10.95. We're going to call it 11 meters per second. Just like that, we're able to solve for a velocity from our conservation energy equation. Okay, we're going to look at another example. In this example, we're going to add some friction to the track. We're going to put a little bit of friction, so no longer will there be a perfect transfer of energy from stored gravitational to all of kinetic. In this case, we'll watch the bar graph and see what happens. And just as we expected, when the guy gets to the bottom of the ramp, He has a lot of kinetic or movement energy, but also this little bit of thermal energy that has been added due to the friction between the wheels of his skateboard and the track. We're going to go ahead and analyze a little bit of quantified information about this example. All right, so this is just like our last example. Skater's up here at the first point, skater's down here at the bottom. But now we've seen we have this thermal energy that's been added due to friction. All right, so it changes our quantitative conservation energy equation just a little bit. We know that the gravitational energy that's stored in the start must equal the energy of movement plus, oh, there should be energy of movement there. That should be gravity. Energy of movement plus now the energy of thermal. So we have this new factor in here, this thermal energy. When we go to expand it, we should see that this is mgh equals 1/2 the mass times velocity squared. There's not an equation for E thermal that we know, so we're just going to keep it like this. Now let's see what would be the amount of thermal energy that was lost if the skater had a velocity of 8 meters per second at the bottom of the ramp. So let's plug in what we know. 75 kilograms times 10 meters per second squared times 6 meters. This right there, that is our stored gravitational, whatever that value is. We're going to set that equal to 1/2 the mass of 75 kilograms times the velocity of 8 meters per second, because that's what we're saying, that's how fast he is going, squared, plus whatever E thermal. We're trying to figure that out, so it's a variable. So when we do this, again, well, we can't do the cancellation of our 75 kilograms in this case because we have this E thermal. So we can't do that as simply in this case. So we're going to go ahead and calculate this out. So 75, let me get it up here. 75 times 10 times 6 gives us 4,500. And that's a joule. That's how much gravitational energy is stored. 1/2 75 times 8 squared. I'll start with the 8 squared. 64 times 75 times 0.5. 2,400 joules plus E thermal. So we get, this is how much kinetic energy there is when he's at the bottom. This is how much stored gravitational there was at the top. The difference between those is going to be what was lost to the thermal energy. So if we subtract 2,400, both sides, we'll just do it in the calculator. 4,500 minus 2,400. The E thermal is equal to 2,100 joules.